In this video, I am going to discuss Master's theorem. We are going to apply the Master's theorem to solve the recurrence relation. This Master's theorem is the best method to quickly find the algorithm's time complexity from its recurrence relation. And this Master's theorem can be applied to both decreasing function as well as the dividing function. It's very simple and a quick way. Now in this video, let's discuss how the Master's theorem can be applied on the dividing functions. So this is the sample recurrence relation where the dividing function is involved. We are already in so many videos we would have discussed what exactly this n is a, n by b, everything would have discussed. Again, I would repeat here in this video, where n represents size of input, a represents the number of subproblems in the recursion, n by b represents the size of the subproblem, and f of n represents the cost of work done outside the recursive call. And the condition must be here, a should be greater than or equals to 1, b must be greater than 1, and it must be constants, and f of n must be asymptotically positive function. These are the conditions, and this is how the recurrence relation, the dividing recurrence relation would look like. And let's take one example recurrence relation. Let's take this recurrence relation, t of n equals to a of t n by 2 plus theta of n par k log per p n. So here the condition given here in the Master's theorem is a must be greater than or equals to 1, b must be greater than 1, k must be greater than or equals to 0, and p must be the real number. These are the conditions, and this is how the recurrence relation would look like, right? And when it comes to Master's theorem, we are supposed to remember only these three formulas, these three steps, where if a is greater than b par k, this formula is applicable, and this is going to be the time complexity. The left hand side, this is going to be the time complexity. When a is equals to b par k, again under a equal to b par k, there are three different cases are there. You have to check the p value. If p value is greater than minus 1, this is the time complexity. If p value is equal to minus 1, this is going to be the time complexity. If lesser than minus 1, this is the time complexity. And the third case is if a is lesser than b par k. If a is lesser than b power k, again two different cases are there. If p greater than or equals to 0, this is applicable, and if p less than 0, and this is applicable. So we are supposed to remember only these three cases in Master's theorem. We can simply and quickly derive the time complexity from the given recurrence relation. And one more thing is, the complexity here under the Master's theorem would be expressed only with the theta notation, theta asymptotic notation. So we are supposed to express it in terms of theta only, not in terms of O, big O. Let's start solving the example. Let me take the first example. T of n equals to t of n by 2 plus n square. This is the given recurrence relation. We are supposed to apply Master's theorem. So here we can use the recurrence tree method to derive the time complexity from this. But since we have the easiest way, the Master's theorem, to derive the time complexity, let's go with the Master's theorem and check. So this is how the recurrence relation would look like. This is the given recurrence relation. Let's derive the values a, b, k, and a, b, k, and p values we are supposed to derive. A is the coefficient, right? The number of subproblem. A equals to 1 here, and b value is 2. K values, this power value is going to be the k value is 2, and p value, there is no p value here, so it is 0. So we have fetched all these four values a, b, k, and p. Now you are supposed to check a and b of k, whether a is greater than b of k, a is equals to b of k, or a is b par k, or a is lesser than b par k. We are supposed to identify. A value is 1, check a value as well as b par k value. Here a value is 1, b value is 2, and k value is 2. So a equals to, you have to check whether a equal, lesser, or greater. If you check, yes, a is lesser than b par k. 1 is lesser than 4. So the condition given here is a is lesser than b par k. If a is lesser than b par k, case 3 is applicable. according to Master's theorem. Case 3 is applicable. Check case 3. If you check case 3, again there are two different cases are there under case 3. You have to check whether p is greater than equal to 0 or p is lesser than 0. If you check p is equal to 0, right? P is equal to 0 means case A is applicable, right? Case 3A is applicable. Case 3A is t of n equals to theta of n par k into log par p n. Let's substitute to the value n. K value is 2 here, so n par 2 into log p value 0, so log par 0 n. Since here it is 0 log par 0, this term would become 1, so the complexity is going to be theta of n square. This is the final complexity. So directly with the help of the formulas, we can derive the time complexity from the given recurrence relation. Let's discuss few more examples. Example number 2. Example 2 is t of n equals to 2t n by 2 plus n log n. This is the given recurrence relation. Let's write a value. A value is 2, b value is 2, k value is 1 and p value is also 1. Now we are supposed to check a value and b par k value. A value is 2, b value is 2 and k value is 1, which means a is equals to b par k. If so, case 2 is applicable. Case 2, if you check the formula 2, under again 3 different cases are there. It's based on the p value. You have to check whether p value is greater than -1, equal to -1 or less than -1. If you check the p value is equals to 1, which means p is greater than -1. So case 2 A is applicable, 8th formula is applicable. So if you check case 2 A formula, it is t of n equals to theta of n power log base b a into log par p plus 1 into n. This is the formula. Let's substitute the formula now. Let's substitute the values in the place of a, b, k and p. N log b value is 2, a value is also 2, so n log to the base 2 into log p plus 1, p value is 1, so 1 plus 1 is 2, log square n. Now if you check n log to the base 2 would becomes 1, so this entire term would become n now, n into log square n. So this is the final complexity for the given recurrence relation. Let's discuss the third example now. Example number 3 is t of n equals to 2t n by 2 plus n by log n. So this can be rewritten as 2t n by 2 plus, here n by log n is there, right? This can be written like this. N by log n is n into log per minus 1 n. This can be rewritten like this. Now fetch the value of a. A value is 2, b value is 2, k value is 1, p value is -1. Very first step is check a and b par k value. A value is 2, b value is 2, k value is 1, which means a is equals to b par k only. Second formula only, case 2, and under case 2 again 3 different formulas are there. Check the p value. P value is equals to -1, which means case 2b is applicable, right? Case 2b formula is t of n equals to theta of, sorry I missed theta here, theta of n par log base b a into log n. So theta of n power, substitute the values, b value is 2, a value is also 2, which means this would become 1, log to the base 2 would become 1, and log n. So finally it would be n into log n. This is going to be the final complexity. Let's discuss few more examples also. Example number 4. Example number 4 is T of n equals to 3t n by 2 plus n square. Fetch the values. A equals to 3, b value is 2, k equals to 2, and there is no p value, so it is 0. Check a and b par k. A value is 3, b value is 2, k value is 2, which means a is lesser than 4. 3 is lesser than 4, which means a is lesser than b par k. A lesser than b par k means k is 3. And again there are two different cases. Check whether p is greater than or equal to 0, less than it's 0. P is greater than or equal to 0. So a formula is applicable. T of n equals to theta of n par k into log par p n. So here k value is 2, so n square, log p value is 0, so 0 n, which means it is n square. This is the answer. So the Master's theorem is very simplest way of to derive the recurrence relation. So it is applicable on both the dividing function as well as the decreasing function. Next example is let's take this one. T of n equals to 16t n by 4 plus n. Now a value is 16 here, b value is 4, k value is 1, and there is no p value, so it is 0. Check a and b par k value. A value is 16, b value is 4, and k value is 1, which means a is greater than b par k. A is greater than b par k means there is only one formula, which is T of n equals to theta of n log to the base b a. So theta of n log b value is 4 and a value is 16. So if you derive this, it would be log 4 base 16 is going to be 2. So it is n square. Next, the final example. Let's solve this. T of n equals to 4 par n t n by 4 plus n cube. Can you try this out? Whether the Master's theorem is applicable? What is the condition given here? The condition given here is a must be greater than or equals to 1, right? And this must be constant also. If you check here in the given example, the a value is 4 power n, which is not a constant. The condition is, according to Master's theorem, a must be constant. Since it is not constant here, a value is not constant here, Master's theorem is not applicable. Master's theorem cannot be applied. So you have to check whether it satisfies the condition first, and then only you should go for picking up the formula which is going to be the appropriate formula to apply. This is how we are supposed to derive the time complexity from the recurrence relation using Master's theorem method. In the upcoming video, I will discuss how Master's theorem can be applied on the decreasing function. Here in this video, we discussed how the Master's theorem can be applied on the dividing function. In the next video on decreasing function, how this can be applied would be discussed. Thank you.